Welcome to this class. We will continue our discussions on the maximum margin classifier or support vector machines. A quick recall, last time we constructed the primal problem of optimization in terms of the parameters of the linear discriminant function, and we said that this problem will be solved in the dual domain. Okay, so constructed, we were at the path towards constructing the dual problem for the optimization, primal optimization problem that we had. That's where we were. So the definition of a dual optimization problem is that first we have to solve this infimum problem, that you take the Lagrangian and solve the infimum problem to get what is called as a dual function. Once you get the dual function, construct the dual optimization problem as the maximization of the dual function with respect to the Lagrange multiplier. So now the variable of optimization becomes the Lagrange multiplier itself. Okay. So please note that here, to even construct the dual problem, okay, or the dual function, an optimization problem has to be solved first, correct. Okay. So now let us continue there. We will just construct the dual optimization problem and then try to solve it. Now what we have to do is q mu, the dual function. First we will construct the dual function. Q mu is the infimum over the Lagrangian. Lagrangian is half W transpose W plus the sum over the constraints W transpose Xi plus B. Yeah, we will have to take the infimum with respect to the variables of optimization in the primal problem, which is W and B. This is the definition of the dual problem. Now please note that we are now looking at the infimum of this objective, okay, with respect to W and B. Now if you look at the objective function, there is observe the term product of mu I, yi, bi. So we have this term, right, inside the objective function. There is mu I, yi and bi. We see this here. Now this is a function of mu. So now if we do not have any constraint on this, then this infimum is unbounded, right. What does it mean? So you can choose a b and a mu such that the infimum is minus infinity, okay, which means that this problem cannot be solved in an unconstrained way. We will have to constrain it. So how do we constrain? So the way to constrain is that you will have to solve this infimum problem, which observe this term which can drive the infimum to minus infinity, which is undesirable. Okay, therefore solve a constrained version of it by forcing the product of mu I times yi, make this to be 0. If we drive this to be 0, then you cannot choose a b such that this problem has a solution that goes to minus infinity. I mean, you are making it bounded. So to obtain the dual problem, we will have to ensure that we not only solve the infimum problem, but we solve it with a constraint that this product goes to 0. Okay. So what to solve this problem, so to solve the constraint in minimization problem, how do we look at the infimum of a particular function? See, and the infimum or the minimum here is with respect to W and B. Okay. From the duality property, right, which is if W star and mu star are feasible for prime and dual respectively, we know that the optimizers for both of these functions are the same, which means that this q mu will attain infimum at w equal to w star, where w star is the optimal for the primal problem, correct. So what we should do is that to solve the above problem, substitute t substitute substitute w star to be equal to I over support vectors. What is that? Is it mu I yi xi, correct? This is the one, and b star, the optimal b star. I leave what the optimal b star is. Please do the algebra and find out what the optimal b star is for the primal problem, or rather let me just write that down. The optimal b star would be, maybe do it, it's good to have homeworks. So find out what the optimal b star is for the primal problem. So we substitute that b star and w star in q mu, we get our q mu to be which is the infimum. See, once we substitute w star and b star or w and b to be w stars and b star, which are the solutions for the primal problem, we are actually getting the solution for the optimization problem. Which optimization problem? The infimum. So what we get is the infimum. So q mu will look like this. It will be a sum over this minus half sum over I, sum over j, mu I yi mu j yj xi transpose xj. So once again I want you to complete this algebra. What should be done? Find what w star is, the optimal w star is, and I mean we already have what optimal w star is, we have find what b star is, plug them both into this particular equation, okay, and expand the terms and drive the product mu I yi to be 0, okay, and if you do that the algebra works out to be like this. Please complete it, it's simple algebra, just do it. So what is to be seen is the following, right? The observation is that in the dual problem, okay, I will write that in the dual problem the data x only appear as inner products. This is a notable point, we will use this later. What am I saying here? Look at the dual problem, right? The dependence on data x term is only as inner products here. Take a pair of data points xi and xj, compute the inner product between them, and that is what appears in the dual problem. Remember last time I told you that sometimes solving the dual problem is easier in the in optimization scenarios. This is one of the reasons why this is the case. Now in some cases, as we will see later, computing inner products is easier than computing the data points themselves. I'll tell you why that happens in a while, but this is an observation to be made that in the dual problem the data appears only as inner products. Okay, actually I can quickly run through the algebra, right? Where is this inner product coming from? It is coming from this w transpose w term, because w is linear in x, right? So therefore w transpose w will be quadratic in x, therefore and since you have inner products in w, that will translate to having, translating into inner products in x. That's how it comes up. Okay, okay, so this is the dual problem now. So let's write down, so sorry, this is the dual function. Let's write down the dual optimization problem. So the dual problem is maximize q mu, which is sum over mu I minus half ui mu j wi wj xi transpose xj. So we have the constraint subject to all mu I are uh, non-negative. We also have another constraint that this has to go to 0. So this is the final problem that we have to solve, and this maximization is with respect to mu. This is the dual problem. Okay. Now if you look at this problem, right, the above problem is quadratic in mu with linear constraints, isn't it? This problem is quadratic in mu, correct? Because you have the product terms mu I mu j kind of terms which are quadratic terms, and there are linear constraints on mu. Okay. In optimization theory, this problem is known as the quadratic programming problem with linear constraints. This is a QP problem with linear constraints. Okay. Now how do we solve a QP problem with linear constraints? If you studied optimization theory, if you have a QP problem with linear constraints, there are standard solvers to solve it. Okay, there are methods to solve this. Let me not go there. So there is one of the algorithms to solve this is called sequential minimal optimization, SMO. Standard QP solvers. For instance, sequential minimal optimization, SMO. Okay, that's it. So I will not go to the details of how to solve a QP problem. Okay, so assume that I am assuming that there are solvers that would solve a, a standard quadratic programming problem with linear constraints. One of the algorithms is called SMO. Okay, and there are libraries to do this. One of the famous libraries that is used to solve this problem is called libSVM. It's I think it is originally written in C, and now there are Python wrappers and so on. Right? Okay, so where actually this solves this particular problem. Given uh, a QP problem with linear constraints, it implements SMO to get the solution for this particular problem. Okay. Now what happened? Given a particular problem, a classification problem, what do we do in SVM? Construct the primal problem. From primal problem, construct the obtain the dual, solve the dual as a QP problem using standard solvers and get your mu stars. Okay. Once you get the mu stars, so we have obtained mu stars right now by solving this, right. So once mu stars are obtained, okay, find W star, which is what we want finally to be correct. This is what it is. And similarly, you get the B star as well. So this is what we wanted finally. We have the mu star from the solution of the SMO problem, the dual problem. Use that to get your W star. That's it. So you have the final discriminant function. Okay. Now we have already defined what support vectors are, right? S these support vectors are those data points for which the corresponding Lagrange multiplier is strictly positive. We have defined it already, right? And the sum or the final parameter will be a sum over support vectors, because the other terms will anyway go to 0. Okay. Now observe another interesting thing, right? So from one of the KKT constraints or KKT conditions, we have something called complementary slackness. So which actually says that you take the Lagrange multipliers, multiply it with the constraints, we have this, right? This is called complementary slackness. Now for those mu stars which are non-zero, okay, what will happen for support vectors? What will happen? We have yi times w transpose xi plus b is equal to 1. Okay. What does this mean geometrically? Geometrically it means that the data points that lie on the margin are support vectors. I mean, now you know why they are called support vectors, right? It's like they are the ones upon which the margins are supported. Okay. So by complementary slackness, what we have just shown is that support vectors are the data points that pass through the margin. So in our here in the construction where we are assuming that the data is linearly separable, okay, the maximum margin classifier is the one that we obtain by passing the margins through the farthest data points, or rather the closest data points from each classes from the decision boundary. You understood? In the, if we go back to our figure, so we need a data point here. Yeah. So these are support vectors. There are 3 plus 1 4 support vector. So the margins will pass through those data points that are the closest to the decision boundary. That is the idea. Is that all right? Okay. Okay. Now we'll have to move on to the next case. Any questions on this? This is the most basic formulation of support vector machines. Okay. I mean, if I have to just run through a summary, we are looking at data that is linearly separable. Okay. And if the data is linearly separable, and we are looking at linear discriminant functions. Now, if the data is linearly separable and we are looking at linear discriminant functions, there are infinite discriminant functions that are possible. Amongst all possible discriminant functions, the question that we are asking is, give me the one that is optimal in the sense of maximizing what is called as the margin. Okay. We formulated the problem that way, and it turned out to be an constrained optimization problem on the parameter space. And to solve that problem, we constructed a dual problem in the Lagrange multiplier space, where the dual problem becomes a quadratic programming problem with linear constraints that can be solved using standard QP solvers. Once we get that, we use those optimal Lagrange multipliers and get back to the primal problem and get the decision boundary, the optimal W star or the discriminant function, and that happens to be the one that passes through the data points from each class that are the, uh, the closest to the decision boundary. Okay, or the ones, and those points are called the support vectors. Basically there is no point, there is no data point that is within the margin. So there can be data points on the margin, there will not be any data points between the margins. Okay, any questions on this? Yeah, it is necessary to get it from both the classes, because see here, if you remember from the previous class, yi can take +1 and -1, right? Look at this equation. If yi takes -1, then those support vectors correspond to one class, and for y equal to 1, it corresponds to the other class. That is how we have defined the margin, right? It's always the case. And okay, and remember this, in the maximum margin classifier, the optimal parameters for the decision boundary is a linear combination of the support vectors. scaled by Lagrange multipliers, and of course there is this class also, right. In any max margin classifier, the optimal decision boundary is a linear combination of the support vectors scaled by the Lagrange multipliers, the corresponding Lagrange multipliers. Okay. Right. So now we have to improvise on this. There are two questions that are to be asked. The first one is, what happens if the data is not linearly separable? Okay. The second question is, can we extend this to decision boundaries that are not linear? Can we extend this to cases where the decision boundary happens to be some function of data, right? Now, if we can do it, if we can solve for both these cases, then we solve the most general case, right? Because if data need not be linearly separable and decision boundary can be any of any form, it need not be linear. So let's take one thing at a time. So let us look at the case where the data is not linearly separable, SVM. We will stop here and continue in the next lecture.